In this video, I will solve a problem where I will use the hydrostatic pressure equation. And before I do that, I want to go over, I want to do a quick review of what the symbols mean here in the hydrostatic pressure equation. For D, we use D for depth. So this is how deep you will go in the fluid. You're familiar with the constant G for our planet. Roughly, this will be 9.8 meters per second squared. This is the Greek letter rho, and this represents the density of the fluid. So here, I want to point out both words, depth and density, start with a D. So I use D for depth, and for density, I will use the Greek letter rho, that is also often used for density. Now, P and P naught, they're both pressures, but they are two pressures at two different points. This is a pressure, and this is also a pressure, but the difference is that the first pressure, the P naught, this is at a higher level than the pressure P. So this pressure is at the depth D. Okay, so always remember that this P naught pressure, this is the pressure that you get at a higher level than the pressure P, which is the pressure at the depth D that you use here. Okay, this is important to remember. Now, moving on to our problem. What I have here, this is a tube that has this shape, and it is filled with water. So this is H2O. Now, this end over here is open to air. So this is open to the atmosphere, but this one is closed. There is no way the water can go higher than this. As I said, it is filled with water, and from here, from the top level of the water all the way to the bottom, we have a distance or a height, whatever you want to call it, of 1 meter. And then D2, this height is 0.8 meters or 80 centimeters. Now, you will always be able to use these constants. You will always be able to say that the pressure in the atmosphere, at least on the surface of the planet, is 101,300 pascals, 101 and 300 pascals. And you will always be able to say that the density of water is 1,000 kilograms per meters cubed. Okay, this is the density of water, which is the fluid that I have here. Now, what we want to find, what the problem is asking us to find, is what is the pressure of the water at this point. So my goal is to find the pressure here. Now, if this was open to the air, as this part of the tube is, I could say that the pressure here is exactly equal to 1 atmosphere, because this is open to air. The pressure here is exactly equal to 1 atmosphere. Now, unfortunately, this part of the tube is not open to air. This is closed, which means I cannot really claim that the pressure here is 1 atmosphere. In fact, it will not be 1 atmosphere. Now, in general, the strategy that we will follow in this kind of problems is the following. We will start from a point where we know the pressure, and then we will make our way through to the point where we need to find the pressure. For example, Here, I know that the pressure on this end of the tube is 1 atmosphere. So my overall strategy will be the following. I'm gonna go from here, where I know the pressure, to here. So this will be, let's call this point A. Let's call this point B. So I'm gonna go from A to B, and then I know, as I've shown you in a different video, I know that the pressure of 2 points at the same height, those two pressures are the same. So I'm gonna call this the pressure C. Okay, my goal is to find, in this problem, the goal is to find the pressure C, and my strategy will be to go from pressure A, I'm gonna find the pressure of B, and from that I'm gonna find the pressure of C. Okay, this is the big picture of what I will be doing. Now let's call this equation 1. As I said, I know that the pressure at A is 1 atmosphere. So we got 101,300 pascals. Now, next step, I need to find the pressure at B. I'm gonna use equation 1. This is the hydrostatic pressure equation, and remember, this pressure is the one that's at a deeper level. For me, I have A and B. B is the one that is deeper, so the left side is PB, okay, because point B is deeper at a lower level than point A. And because A is higher, I'm gonna say PB equals PA plus the density of water times 9.8 times the depth. Now here I need to do a little bit of work to see what depth I'm gonna use. Remember, I'm going from A to B. The depth that I need to use is the depth of B. And since we're looking for the pressure at B, I'm gonna start using the numbers. The pressure at A is 101,300. The density of water is 1000. G is 9.8. And then for the depth, I'm going from A to B. That means I have 1 meter here and 80 centimeters. That means the depth is 20 centimeters. And if we do the result, the calculations, we will find that the pressure at B is 103,260 pascals. And this is the pressure at B. Now, as I said before, I'm going to go from A to B, and I did that. I know the pressure at A, I found the pressure at B. Now from B, I'm gonna make my way through to finding the pressure of C. But I want to remind you, I've said before, I've shown that the pressure at B and C needs to be exactly the same. I've shown that. So once you find the pressure at point B, you have also found the pressure at point C. So the pressure at C will be 103,260 pascals. So this is the strategy that you will use in these kind of problems to use the hydrostatic pressure equations. You will need to start from a point where you know what the pressure is, and then make your way through to the point where you're looking for the pressure. And just be careful. Remember that the pressure on the left side of the hydrostatic pressure equation, this is the pressure at the depth D. This is the pressure at a level higher than this.